Okay, in this video, we are going to do a very basic one sample hypothesis test for proportions. The Research Center claims that 25% of college graduates think a college degree is not worth the cost. You decide to test this claim and ask a random sample of 200 college graduates whether they think college is not worth the cost. Of those surveyed, 21% replied yes, that it was not worth the cost. At a 10%, at alpha equal to 10%, is there enough evidence to reject this claim? So I want to spend a little time deciphering what we have here before we start plowing into our steps. Okay, so the Research Center is claiming that the population of all college graduates who think the college degree was not worth the cost is 25%. You are testing this claim. You're not testing you think it's more or less. You're just testing, is it really that or is it not that? So you do your own sample of 200 college students, and within that sample you come up with 21% replied yes, they felt like it was not worth the cost. So this 21% is your p-hat. It's a result of your survey or your sample. This 25% is the population proportion that we are testing. So that's going to be really important that we get those straight. Always the data that is, or the summary statistic that is coming from your sample is your sample statistic, or your p-hat in this case. So as far as the first two steps, the textbook and your MyMathLab will ask this question, so I want to lead in with it, but I usually kind of skip past it. The claim is that 25% of college graduates, the population of college graduates, think a college degree is not worth the cost. So that tells us that our population proportion is equal to 0.25 for this hypothesis test. But you will need to start in with step 3 for sure and be able to provide these for me on an exam. Our null hypothesis is, again, always going to have that equality. So our population proportion is equal to 0.25. That is what the claim was. Our alternative hypothesis is the inequality, that the population proportion of college graduates is not 25% who think that college is not worth the cost. Okay, so we've got those squared away. Step 4 came from this last portion here, at alpha at 0.10. So that automatically links with is the complement to 90% confidence level. Again, I'm repeating, alpha is at 0.10. This is a two-tailed test because of this inequality sign here. It's not greater than, it's not less than. That would be a single tail. We're going to have this 10% split between the two tails. So this is a two-tailed test. The z-score that correlates with that is a plus or minus 1.64, and I got that from a number of places. So you could go to your formula page. It's organized very nicely on our formula page here. We were doing 0.1 alpha, and this was a two-tailed test. All confidence intervals are two-tailed tests, so the z-score that we use when we're calculating is plus or minus 1.645. Another place that I could look for it is, if you remember in the notes when we first started into confidence testing and hypothesis testing and confidence intervals, we brainstormed this whole chart of tails that I wanted you to be able to picture and see what was going on. So again, confidence intervals are in the center column here. It's a two-tailed test. We're looking at this first one where we're going to, the 90% in the middle are the usual outcomes. And that 10% that is our alpha is split between these two tails. So if we get a test statistic that correlates with the z-score that is out here in the tails, that's going to tell us something is significant, that we have significant results. If we get a z-score from our test statistic that falls inside here, that is going to be normal. That's what we're testing for. Okay, so back to our notes. When we set up our test statistic, this is the formula that we use, and again, that formula will be in your note page. This is that formula right here. Okay, I keep flipping back and forth. Hopefully you're following me. So our formula is here. I will need for you to plug in things correctly. I need to plug in 0.21 first. Remember, that's our p-hat, and that came from here. 0.21 minus 0.25 over a square root of our Q and, sorry, our P and our Q, and these are P and Q from the population. Notice there's no hats right here. So this is from the population over the sample size. So this is really kind of the mix of information that we have here. We come up with a test statistic of negative 1.31. That's not very, I mean, we know that that is actually falling in the center range, if you can kind of picture that. That's not as extreme as our critical value, that borderline. But I want to go on to the next thing here and show you the results of our next 3 steps. Hopefully I didn't lose too much there. Okay. If we're using the critical value method, you need to draw the curve. You're going to place your critical values here. We had negative 1.64 and positive 1.64. Our test statistic fell inside that range. That's in the usual range. So we have nothing unique here with our sample. Our sample falls in line with that population proportion being equal to 0.25. When we do our p-value, notice that when we plug in the probability that correlates or is associated with the z-score that is less than negative 1.31, we get this 0.0968. But that's only the probability that's in one tail. This is a 2-tail test, so we have to remember there would have been another tail over here that would have held another 0.0968. So we have to double that amount. Okay, so this is using the P from the Z table. So we have to double because we have 2 tails. If I went into StatCrunch, I did it in StatCrunch and came up with 0.1914. But either way, that falls inside here. That p-value falls inside here. If we were going to do the confidence interval check, again, now this is where I actually would use the p-hat. P-hat, remember, was 0.21 plus or minus the 164, and you're like, how did I get that z-score again? You need to remember we got that from our formula page. We were doing a 2-tailed test. This is a confidence interval with 2-tailed. Back to our notes. And then we're plugging in the p-hat and the q-hat. This time it's 0.21 and 0.79. So the confidence interval uses p-hat, q-hat. Our test statistic uses our population proportion, P and Q, not our p-hat. Okay, when we plug that in, we get this range of 0.163, 0.257. We're like, what's that even mean? Sorry, I keep flipping back and forth here. I'm trying to get to where you can see the null hypothesis. We're testing is a true population proportion equal to 0.25. 0.25 falls in this range. So we can't really reject the null hypothesis. That null hypothesis falls in our confidence interval range. So all 3 of these are saying that our test statistic fell within the normal range. So we really can't reject the null hypothesis. So our outcome is to fail to reject the null hypothesis. That's our decision. And our conclusion is there's not enough evidence to reject the claim that 1/4 of college students do not feel that a college degree is worth the cost. So I would like to do this on StatCrunch for you, but it's going to take a little bit of maneuvering my screen. Whoa, you probably can't see that. Okay, so let's try this again. Okay, I want to move my, guess I can't. Thought I could center this, but I won't be able to. So when I go in here, I'm going to go to Stats. So I'll make this a little bit bigger, but I'm going to go into Stats. I'm doing proportion stats, 1 sample, and I have summary information. Okay, the thing that's unique about this is, I hope that you can see this to some degree, the number of successes. You have to put the raw summary statistic data in here. I had 21% of 200 people involved in my survey. So if I do 21%, 0.21 times 200, I had 42 successes. So I need to put that raw information in there. 42 successes out of 200 people who were surveyed. And I'm doing a hypothesis test. It's defaulted to hypothesis test, so I'm going to leave it there. I am testing the true population proportion. We're thinking it could possibly be 0.25, so I need to put 0.25 in here. There's nothing else I need to do. I just need to do my number of successes, number of observations, and what my population proportion is. The other thing that I really should check is I'm testing to see that the population proportion is not equal to 0.25. That is my alternative. So those 4 things I need to double check. So then I hit compute, and this chart tells us all our information. I knew this, the sample proportion, we knew that. The z-test stat is confirmed. Negative 1.31 is what I rounded mine to. And then the p-value is 0.1914. So that helps us with, this helps us with our critical value to plot that. This helps us with our p-value method. Okay, what if I want to check the confidence interval? So I need to go back to options. I'm going to click edit. And this time I'm going to go down and I'm going to click that I'm looking at the hypothesis. It's not the hypothesis test, but the confidence interval. So I click this and I'm looking at a 95% confidence. Actually, our problem was 0.9. So I need to make that change in there. The confidence level, I didn't need to take into account with the hypothesis test. I evaluated that when I looked at my test statistic and my p-value. Sorry, I'm trying to move this so you can see what I compared this p-value to what I knew was my 95% or 5% alpha. Okay, but here I need to put in the confidence interval for 0.9. So I click compute, and it is going to show me my confidence interval. My lower limit was 0.1626. My upper limit was 0.2573. Okay, remember 0.25 did not fall in this range. So again, that all of this from StatCrunch supports what we came up with doing this by hand.